Now this is the command window of our Matlab online. So in this video, let's implement how to use our M files in order to calculate for the terminal velocity of our falling parachutist. First, using the analytical method, then the numerical method. To start, let's have a new script. So this in this editor where we write our program. This is our command window. This will be our editor for our program. Okay, so for the analytical, I already prepared here our program, our initial program, which should be editing. Okay, so having this, okay, this is based on this, where we are to have our mass, our drag coefficient, then our step size, here it's 2, then our initial time, and our final time. Then later we'll be calculating for the terminal velocity. Okay, so that's why we have this. And then, okay, so this one, this is actually this one. Okay, let's try. So let's name this as analytical parachutist, analpara. Okay, so have you seen this? Let's enlarge the command window. Okay, so as you can see, this one, V at 6, it's 35.64. Yes, V at 12, 47.49. Okay, so we have checked that the results of our program is correct. Now, okay, let me explain a little. What happens is, after we initialize our variables, so it then enters this while loop. So it carries out these operations, then it prints fprintf, prints this at our command window. So %d means it's a decimal. Then this does not print %d, but the value of your first source. This will be the source of your %d. Then this one, %f, it means it's a float, and it will get the value of your v. So this is, if this first occurs, then it will also assume the first variable. Second, then it will assume the second variable, and so on. Okay, this is /n. This is for a new line. Then it will update the time. So initially it's 0, then we got the velocity at 0, then we print the velocity at time equal to 0, then we update. That would be 2. Then our condition that we will stop our iteration is that when the time exceeds our final time, which in this case is 12. So if it exceeds that, we'll break the loop. So this break command will terminate the loop, and our program will then exit this loop. Okay. Now what if let's try now to make a function for our velocity. Instead of doing this in our main, let's do this. Let's make a function which we can call from time to time. Let's make a function. Let's say the output variable is vel. The name of our function will be velocity. Our inputs will be m for the mass. Then let's have the cd for the drag coefficient. Maybe let's just use c. Okay. Then because it's c here. Okay. Then let's have the time t. Okay. Then we'll have this one. Vel is equal to this g times m over c times one minus exponent negative c over m times t. Oops. Times t. Okay, so semicolon. exp in Matlab, it means e, this one, e. Then this one inside your parentheses will be your exponent. So that's the syntax in Matlab. Okay, so we'll have in this line, let's call the function, and let's have mass. Did we use mass? Yes. F drag coefficient. Okay, yes. Then that time. Okay, let's try this. Oops. There's an error. Unrecognized function or variable g. So a while ago, before we created our function velocity, we have our g here, which we use for our v here, for our previous expression. Now, the variables in your main can't be seen in the variables of your in your function. So that's why, even though we have already initialized g here in your main, there's an error. That is, it says unrecognized variable g. Okay, since we won't be using g here in the main, then let's just take this out and transfer this one to to our function. Oops. Okay. Now this also shows and illustrates that the variables here are separate from our variables here. That is, even though we have declared and assigned values to our variables here, just a while ago we just had g here at this spot, so we can immediately use that in our function. Okay, so let's try this one. Okay, so that's it. We have okay, we have these values. Okay, now let's try to give the user the freedom to change the parameters. That is, we'll ask for his input. So for that, let's use this input function. Mass. So a while ago we had our user defined we have created our own function, velocity. Then this one, let's have input, this will be in kilograms. Then let's have drag coefficient. Let's drag coefficient. Oops. In kilograms per second. Then let's have input also here and here. Step size in seconds. Then let's have the time. Still in seconds. And the final time. Okay. Okay, let's try this one. Okay, so as you can see, it now asks us to input the mass. So therefore we can now, the user now has the freedom to change the mass. Okay, but this time let's just still try what we had a while ago in order to check step size of 2, time of 12. So as you can see, we still have consistent answers. Now let's try to change. What if the mass is 100? The drag coefficient is let's say 10, step size of 1, then let's have 10. So we have this v at 0 up to 10. Okay, you might wonder why this is not consistent. It's because we have changed the parameters. Okay, so this is just to illustrate that by using this one, this input command, we can now vary our parameters. Okay, now let's have, okay, what if we'll have this one, still 68.1, 12.5, step size of 2, initial time of 0. What if I wanted to find the velocity not at 12 seconds but at, let's say, 12.7 seconds? Now you might observe that our program has just given us v at 12, though the answers were correct. However, it failed in giving us v at 12.7. So let's try to check our program. Why is that so? Now at time, let's say at time equal to 10, so 10 plus dt, that is 2, that will be 12. Then this is false because this is 12.7 and this is 12, and it will return here. Then velocity at time 12, so it will go to this function, then print the velocity at time 12. So that's why we have it here. Now at time equal to, this one is 12, so 12 plus 2 dt, that's already 14, and 14 is greater than 12.7. So since it's greater than 12.7, so it will break the loop, it will terminate the loop. That's why we were not able to have the velocity at 12.7 seconds. And this shows that we need to do something to our program so as to adjust dt. Okay, so how are we going to do that? Let's have this condition: if time plus our step size, if the if that is greater than our t final, then we will adjust our dt to time t final minus our time. Okay, so in this way, if we have a time equal to 10, let's say a time equal to 10, this one time equal to 10, so 10 plus 2, this will be 12. Now this is still, if we have 12.7, t final as 12.7, this is 12 now, 12.7, so it's false. It will come up here, then it will try to test 12 plus, it should be step size, 12 plus 2, so that is 14, which is greater than 12.7. So this will adjust our dt. That is t final 12.7 minus time 12. So that's 0.7. So velocity at this is 12 still. Velocity at 12, so it will print the velocity at 12. Then it will have time, that is, this one is 12. 12 plus 0.7, so this will be 0.7. Then it still falls, so it will come up here. dt here will be dt here will be 0. So velocity, it will calculate the velocity at 12.7, then print the velocity at 12.7. Now what happens is dt will be equal to 0, right? So 12.7 plus 0 is still 12.7, and our condition to terminate the loop is if it's greater than t final. So instead of having this one greater than t final, since we know that by adjusting this one, our dt, eventually our time will fall at t final. So let's just have, okay, let me illustrate. If we won't adjust this one, it will result in an infinite loop. Let's try. So as you can see, it was stuck in V12. T final minus time. Okay, yes. Okay. So let's have if time is equal to t final, then if time is equal to t final, no, it should be, if we do this at 12, then adjusted of 0.7, so this will be, so it won't calculate the velocity at 12.7. So this also won't do. Instead, since we know that we are already at the last step when dt is equal to 0, so let's just use that one. So as you can see, we have this one. If ever we did use that one, the time is equal to t final. So what happens is it won't give us the value at 12.7. So that's why we'll use dt equal to 0, because this is our indicator that we are already at the last step. Okay, so what other else? Okay, since we are to have the terminal velocity, let's try to, and we know that we reach our terminal velocity at a later time, so let's try a scene in here. So maybe let's try 100 after 100 seconds. Okay. Okay. Wait. If we will have time at 100 seconds, then we will have 51 lines. Okay, that would be okay. Anyway, let's have 50. This will be very long now. Okay. So at 50, it's starting to be constant, but it's 39, so maybe on 50 it will reach this one, 39, but it's already starting to approach its terminal velocity. Okay, let's try. Wait. Maybe let's just plot. Okay. No, later. We will plot this later. Okay. 68.1, 12.5. Oops. My bad. Invalid expression. It's 12.5. Step size of 2. Let's have it at 100. Okay. So here we can see that it has okay. So it's already 53.39 at this one, 66. So if we are to graph this, so we know that here it's already approaching a straight line. Okay, so therefore we'll have our terminal velocity at this one.